Hello, everyone. Good and welcome again to another stream here on Freaky Physics. Yes, we're still doing the same thing. We're still streaming about exam preparations for the DP. Yes, IBDP exam for physics is in a few days. So for everyone taking it, good luck. All right, and let's get ready and let's get into the class now. Okay, so while we're waiting for the student or Gita, I'm just gonna talk. I hope somebody sees this stream and gets in again. Yeah, I really was like, I was actually excited to see that last time. Right, she's here. Hello, Gita,
Hello.
and good day. How's everything today?
Great. How
Hey,
about you?
doing great. Thank you for asking. All right, okay. Let's. How many problems did you send over today? One.
Couple.
I think I may have double opened some of these. Looks like it.
Mm,
Oh no, these are past papers.
yes,
All right,
Mhm.
I have past papers open. All right, so let's go now to this. Let's start. Okay. Um, let's share my board first before we continue. And where is it? There we go. Okay. You also sent over three more. I don't. That's everything. Okay, so let's start. Uh, okay, let's copy this first. The first one is about the kinetic model. Um, Actually, for this problem, I think you know how to do it, but you did write a question, right? The one you said here by how much, right?
Yeah, I don't really understand how we can know how many particles there are and then how we can estimate
Okay.
how much.
All right. Actually, but okay, before we go there, let me just make sure you've already solved A, B, and C, right? Not
No, I
quite
don't
yet.
know how to estimate the
You
volume
know,
of the
all
room.
right, so let's start with that part then. Let's start with this, okay? Now, the ideal gas, it is the assumption that the volume of the atoms is zero for ideal gas. Okay? Now, if it's not an ideal gas, like if it's a real gas, of course that's not going to be the case, right? But okay, the best way for us to go through here is, well, okay, in A, this is I think we need the answer to the volume of the room, right? Are we talking about the room you're in, or are you given a room, a particular room with dimensions?
I think we have to estimate a room.
Okay, all right. An average room would have what would be the dimensions of a room on average? Let's say a classroom to make it easier, more standard. So, okay, so in this
Yeah.
case, classroom. So that's easy to estimate, right? What's the volume of a classroom? Like, I know it's gonna be 3 meters high. So a classroom generally is shaped like a cube, right? Or a cuboid. And generally speaking, that's 3 meters high in most cases. I'm gonna estimate that this is gonna be 5 meters by 5 meters. Okay, so that's your room, classroom. All right, so we can already say what the volume of the room is, right?
But how do we know it's big enough compared to the atoms?
Okay, We'll get to that in a while, okay? It's gonna be a lot easier for us to actually go through the problems A and B first, okay? A and B first, and then we go to C, okay? All right. So here, the volume of the room, we can easily say that that's just gonna be 3 by 5 by 5, and that's gonna give us 75 cubic meters, right? Okay. The second part here is B. You're estimating the number of gas molecules in the room. You're gonna have to use something in particular here. You're gonna use, for part 2, one of the gas laws. Which gas law would be the best? Okay, this time around, let's take a look at the data booklet. Where's the data booklet? I have it open. There are 2 formulas you can use. One of them would be better. It's under B3. Okay, so you're gonna have to use this law, the ideal gas law. But which version? NRT or NKBT?
I don't know.
Okay, I'll tell you first what they are. N is number of moles. R is the ideal gas constant. Ideal gas constant. Okay. And the big N is number of particles. Okay.
We don't have neither the number of particles nor the mole.
Yeah, but looking at the question, which one are you looking for?
Volume. The number.
Number of
Sorry.
particles, right? So, okay, last one here is the KB. This is Boltzmann's constant. Okay, not to be confused later on with the Stefan Boltzmann constant. Okay. And all of these values, the ideal gas constant and Boltzmann constant, are also in the data booklet. So just look for them later. Okay. So going back, the more useful version is this one, right?
Yeah.
And we're gonna start with that. So what's given to you in the problem here? Well, it's not exactly given, right? But you are in a room. So if nothing else is given, you can say that that's 1 atmosphere. The pressure is 1 atmosphere, which will convert to 1.01 times 10 to the 5 pascals. Okay? So that's 1 atmosphere. The volume, you also don't really have it, but you estimated it in A. So your volume here, your estimate is 75 cubic meters, right? Again, N is, you're looking for N. KB is given. It has a value. Data booklet, right? And finally, T. Well, again, you're in a room, so you're gonna use room temperature. So you're gonna put it here. The temperature of a room is around 300 Kelvin. Okay, so again, if you see a room, these 2 are automatic values. Okay.
Okay.
All right. If it's okay, so from here, just find N straight away. Use the formula, right? So let's just calculate that briefly here. So what do we get? So volume, no, N should be PV divided by KBT, right? So P is 101,000. Temperature is, volume is 75. Okay. Then divide that by the temperature, which is 300. Then divide that further by Boltzmann constant. What is KB according to the data booklet? Let's use the value there. Boltzmann constant. Where are you? Trigonometric Boltzmann constant. There we go. 1.38 times 10 to the minus 23. Okay. So KB is given as that. So we're gonna we're gonna divide that further by where is it again? Boltzmann constant is 1.38 exponent negative 23. Okay, and that gives you the number of particles. What is this? Let's see. 3, 6, 9, 12, 15, 18, 21, 24, 27. 1.83. This gives us n equals 1.83 times 10 to the 27 molecules. Okay. Now, just so we're clear, this is an expected number because you know that molecules are extremely tiny, right? So this should be an expected value. Okay, now let's go to C. Okay, now it says here that the diameter of a nitrogen molecule is approximately 3 times 10 to the 10, right? So how do you get the total volume? So C, what's the volume of all the molecules?
The n times that.
This n, correct, times this, correct. Yeah. So all we're gonna do now is just multiply this value, the value we got earlier, by 3 times 10 to the minus 10. Minus.
Oh, but we have to make it the volume of a sphere.
Mm-hmm. All right, because that's only diameter. You're right. You have to change that to a volume of a sphere. So let's redo that. So find the volume first, right? The volume of the molecule times n, right? You're right. So this is the diameter. We find the radius first. So the radius is 1.5 exponent negative 10. Then we're gonna square that, right? No, not square because volume. We're gonna cube that. Okay. Cubing that, that's their answer on the calculator, and then we multiply that by 4/3 pi. So times 4 divided by 3 times pi. Okay, so the volume that we get is gonna be 1.41 times 10 to the minus 29, and our n is 1.83 times 10 to the 27. Okay, so excuse me, multiplying by 1.83 exponent 27, what do we get? We get 0.0258 or 2.59. That would be better, 2.59 times 10 to the minus 2 cubic meters. Now, this is what we mean now by that statement earlier. Compare the volume of the actual gas. The volume of the gas is the whole room, right? It's 75. But if you take all the atoms together and all the molecules together, that's our volume. That's basically nothing to 75.
Yeah.
Okay, so that's why, so that's exactly what this means. Okay. All right. Is that clear now?
Yes.
All right.
It's actually much simpler than I thought.
Okay, great. Let's move on. 12 and 13. So the next few questions after this, okay? Okay. Basically, these the statements that come before the questions, they're the assumptions of the kinetic model. Okay. Now, okay. In A and B in number 12, it's actually asking you to compare the effects of gravity to the actual speed of the molecule, right? So in this case, go back to A. You know the mass? Do we know the mass of the molecule? is not given. Okay. Estimate topic as a gas molecules travels from the floor to the ceiling. Okay, we're gonna have to make a few assumptions here to make it so we can solve. Okay, so we're gonna assume that the average air molecule is nitrogen. Okay, so because we have nitrogen, the average mass would be equal to 28 at 28 atomic mass units. Okay, we're gonna change that into kilograms by using the factor in the data booklet. 1U is 1U is given as, where is it? 1.661 times 10 to the minus 27. So this is going to be extremely tiny, right? So 1.661 exponent negative 27. Then we're just going to multiply that by 28. Oops. 1.661 exponent 28 27, but negative times 28. So that's still going to be extremely tiny. That's 4.65. Okay, what's that going to be? 4.65 times 10 to the something kilograms. How many is that? 26 minus 26. Okay, so again, that's the mass of one nitrogen atom or nitrogen molecule. Okay, so remember, let's say that one nitrogen molecule goes from the top of the room to the floor, from the ceiling to the floor, and we know that's going to be 3.0 meters estimated, right? So what's the change in the GPE here? That's just equal to 1/2. Sorry, not 1/2. Just the mass. That's gonna be 4.65 times 10 to the 20 minus 26 times, let's just say, estimate. So we'll just use 10 and then times the 3, right?
So we just use the same formula.
Yeah, we just use the same formula here. So,
but didn't we, in the kinetic model, we don't use the potential energy?
Yeah, we don't, because the idea here is we are gonna compare the actual kinetic energy to the GPE that it would gain, right? So basically what we get here, this is just a change in the GPE. 1.40 times 10 to the 24, negative 24 joules already, okay? So now, think about it this way. That's the change in the GPE, but we know the kinetic energy of a molecule at room temperature is gonna be large, relatively large, right? How do we calculate the kinetic energy? Kinetic energy, again, data booklet. There is a formula that relates temperature to kinetic energy, right? The formula is, again, average kinetic energy is equal to 3/2 Boltzmann's constant times T. We already know Boltzmann constant from earlier. We know the temperature. That's room temperature. So we put that in here again, right? What's that gonna be? I'm gonna cheat a little bit and just check Google on the actual value, but we can calculate it from here, right? Okay. So anyway, average kinetic energy of nitrogen molecule. Okay, that's gonna be approximately 6.07 times 10 to the minus 21 joules. Okay, so again, cheating off of Google, that's the answer. We can actually calculate this. We'll get a similar value. Now, why am I cheating off of Google instead of calculating? Because it doesn't matter what we do. We get 10 to the minus 21 here. This is 10 to the 24. This is like approximately 1%. Not even 1. That's like a difference of 3. So that's 1,000. That's like 0.1%. Right?
Mhm.
So
And then what does it conclude?
so the change in GPE is like approximately, I'll just write the number first so we can see it, right? Approximately equal to 1/1000th of the kinetic energy. So what that tells us that the kinetic energy is so much bigger than the gravitational potential energy if that molecule goes from the ceiling to the ground straight away with, just a straight path. So if it's moving in a straight path, the GPE increases by less than 1%, then that means it's basically nothing again compared to the kinetic energy, and we can ignore the GPE for molecules of gases. Okay?
Okay.
So this means change in GPE, in other words, is negligible. And we therefore can ignore it. Okay?
Yeah.
Okay. Compared, I'll just finish this up compared to KE. All right. The second question there was, yeah, we answered A and B. Let's go to number 13. So the kinetic energy assumes when they would be elastic collisions. Okay. Again, this is an assumption, and we need to kind of go through why that's an assumption. Think about it this way: if the collisions were inelastic, they would have to slow down, right? The molecules
Yeah.
would slow down. And if the molecules slow down, they lose energy. And if the molecules lose energy, what happens to the temperature of those things? What will happen to the temperature of the gas?
Lowers.
It lowers. And then, because it's always inelastic, what keeps happening? With each subsequent collision, the temperature of the gas goes lower and lower and lower until we reach the lowest possible temperature, absolute zero. Okay? So is that a good assumption? Does that really happen with gases? As long as you don't really touch the gas, does that really happen?
Yeah.
Actually, no, it doesn't.
Why wouldn't it happen?
Okay. If the gas particles lose energy, then at this point in time, then everything should be cold. Nothing should be hot at this point in time.
But the ideal gas model is not correct, like scientifically.
In a manner of speaking, yes. But remember, the reason why we have these laws is that it helps represent the real world. If we follow the laws, it kind of follows the real world more closely than if we didn't follow the laws. In this case, if we didn't follow this idea that this idea of the kinetic model, that the gas molecules are elastically colliding, then that means they are inelastically colliding. They're losing energy. They're getting colder. Everything should be frozen. There should be no gas. Gases shouldn't exist. Yeah? So this is not a good assumption, because if it were, so I'll just write it down again. No, because inelastic means molecules lose energy, right? And then when molecules lose energy, eventually freeze. Gas eventually freezes, right?
So you'd say that in the real world, energy is conserved,
Mm-hmm.
like in the collisions.
Yeah. Okay. So even if the energy was conserved, if the gas loses the energy, then the gas should freeze, and that doesn't happen. If energy were conserved, then it actually goes into the idea that, what's this? That it's elastic. Okay, elastic means molecules don't lose energy. Okay, at least during the collision. Okay, energy during the collision. So, okay, clear?
Yeah.
All right, let's move on. Which one is this? Okay, that's done. Gas loss. Okay, let's not do that one yet. Let's do this. All right, this one now is a calculation question with a word problem. Okay, so you have a container of constant volume. We don't know how much of a monatomic ideal gas there is. When you put 50 joules of thermal energy in there, the temperature increases by 85 Kelvin. So calculate the quantity of the gas in the container and then calculate the mass and the specific heat capacity. Okay. Oops. All right. Let's put it here like this. All right. We don't know the mass. That's all we is that the only thing we don't know? The volume also, but the volume is kept constant. So that should tell you. Okay, first of all, let's take a look here. The temperature is 85K. So delta T is equal to 85, right? And that's, I'm just gonna write that as T2 minus T1. Okay. Okay. What's our what else do we know? The volume is constant, so let's write that here. V is constant. What other quantity matters here? The pressure, but we don't actually need that, but let's just put it in. We don't know the pressure. What else? We don't know the mass. Unknown, right? But here's the thing. We can actually find actually we don't need the mass. We don't need the mass, but we know we're looking for the number of moles. N. Okay. T. Okay. Is there anything else that we need? I think, yeah, we need that energy, the change in the energy, or delta Q. That's going to be 50 joules. Okay. So with that, with everything we need here, let's take a look again in the let's take a look here. That's not gonna be there. Okay. What I'm doing here is I'm looking at the data booklet for the best appropriate formula. I think that's gonna work best with thermodynamics. Yeah, thermodynamics works. Okay. All right, we're gonna have to do the equation for thermodynamics. Q equals delta U plus the work done. Okay. Now, since the volume is constant, then this implies that W, the work done, is 0. Okay. All right. What's the amount of the thermal energy is transferred? So that's going to be our Q. That's our Q. Okay. So this is going to be 50 here, and that's going to be change in the internal energy. Just that. Okay. And thing is, the change in the internal energy, there is another equation in the data booklet that involves temperature. The change in the internal energy is equal to number of moles, so we'll use the number of moles for version, N R delta T. Okay, so we're just gonna put that in here. That's 3/2 N R, then our delta T is 23, right? Sorry, not 23, 85. Okay, we're looking for the number of moles, and R is a constant. We can just find N from there. So from here, N is equal to 50 times 2 divided by 3R times 85. Okay. Boltzmann constant is, so if I do it like this, Boltzmann constant is again 1.38 times 10 to the minus 23. So let's put that in the calculator real quick. That's 50.
Wait, isn't it the ideal gas constant?
Yes, it is. Oh, right, you're right. Why did I say Boltzmann? Ideal gas constant. Okay. That should be 8.314. Okay. So going back to the calculator, so 50 times 2 divided by 3 times 8.314 times 85. Okay, so that's gonna give us 4.72 times 10 to the minus 2 moles. Okay.
And is it a common question that we have to mix these two topics together?
In all honesty, I'm not so sure because of you taking the new syllabus, but basing it from last year's old papers or the papers from the last cycle, I think so.
Okay.
All right. Okay. So, and then the next part B, we're gonna change the number of moles to a mass, given this. Okay. So specific heat capacity. Okay, let's do this real quick now. So that's A. So B, what are we gonna do? First, we need to find the mass, and that's easy. That's gonna be the mass is equal to the number of moles times the molar mass. 4.772 times 10 to the minus 2. Let's just put the unit here first, mole. And then we have 40 grams per mole. So the mole cancels out already. Okay. So all we do now is multiply this number by 40, and that's what we get for the mass. And that is just gonna give us 1.87 grams. So that's our mass. Okay. Now that we know the mass, how do you find specific heat capacity? Specific heat capacity is C. That's gonna be equal to Q all over M delta T. We know the Q, 50. The mass is the 1.87 grams. This 50 is joules, and then the change in the temperature was 85 Kelvin. Okay. Specific heat capacity doesn't have a specific unit. You just use the units given to you. So let's just do that now. Times 50, then divide further by 85. That's gonna give us 3.12 times 10 to the minus 1 joules per gram per Kelvin. Specific heat capacity is like that. Okay.
Okay.
All right. That one's done. That's SHM. That's energies. We can do that later. It's standing wave. All right. Okay. I think you may have a question on this next image. It's the one with the graphs on the gas loss. So
yeah.
Okay. What's the question here?
It's pretty simple. It's just I don't understand what this curve represents because the gradient is the mole.
Mm-hmm.
So is it increasing or like why is the mole increasing?
Okay. PV, yeah, correct. So the y-axis is the number of moles, right? And then there's the pressure here. Now this curve is simply telling us how where's my mouse? Oh, there it is. Okay. Okay. All right, as you said, this is just moles, right? So what does this mean? At 0 atmospheres, okay, let's just do the ideal gas. Okay, at for an ideal gas, it doesn't really matter. It doesn't really matter what you have. Okay, if you have 1 mole of gas and you put it under several under different pressures, you'll get this graph. Okay, so this simply means that for any ideal gas, oh no, not any, but for an ideal gas, it doesn't matter if you have 1 mole of a substance, it can it's a bit weird to say it like this, yeah, but what this means basically is the ideal gas, even if you increase the pressure, no matter how much you increase the pressure, this is going to be the temperature. Hold on, something is weird with what I'm saying. Okay, I think I better start with this. Okay, let's start with this curve, 200K. Yeah? What is gonna happen here? No, that's still missing. There's some information missing. Hold on. Let me just stop myself from talking first.
Okay.
Okay, 200K, that's the curve. For 500K, that's the curve. For 1000K, that's the curve. For ideal gas, it's basically the curve. So, if you start off with 1 mole of gas, that's what this means, at 0 atmospheres, oh, it's still not very clear because this thing, we know that from the ideal gas law, it's gonna be like the number of moles, right? Okay, so if you have 2 moles at 600 atmospheres, okay, so this is what it means, I think. Hold on. If you have any gas at 200 Kelvin, if you have a gas at 200 Kelvin, 2 moles of the gas would give you 600 pressures, 600 atmospheres of pressure. Okay, same thing if you're using that 200 Kelvin temperature of the gas. So once you go into 1 mole of the substance, its pressure is gonna be here. That's gonna be around, what was that? That looks like around 400, right? Okay, so let's take a look here what this means again. For 200 Kelvin gas at 150 atmospheres, the number of moles needed to get there is there. Number of moles needed is half a mole. All right. So basically, these curves just tell you how many mole, what the pressure is for what the pressure of for a particular temperature. So these are your temperatures, right? So we will ignore this ideal gas for now here. So when you have these temperatures, you would use these curves to predict the amount of gas that you have for a certain pressure. Okay. In this case though, the weird thing here is because the n here is not expressed in n, but it's expressed in PV over RT, right? Okay, so what does this mean here? This means that since pressure decreases, then the volume could also change depending on how this curve looks like. Okay, yeah, that makes sense in my head. That makes sense. But basically, what it's telling us is that for different temperatures and different pressures, because we're not using N anymore, we're using PV over RT. These would be the corresponding values for PV over RT if you have these temperatures and this pressure. Okay. Now, ideally though, if the pressure keeps increasing, the volume should also increase with it. Right? So if you graph the ideal gas for the PV over RT, you're always gonna get this straight line. In other words, the volume and the everything here, the PV and T would basically cancel each other out for an ideal gas. But here's the thing, I just want to make this clear. With lack of a context, this is the best I can think of. Okay.
Okay. So the blue curve is the ideal gas, and the green and purple is
no, the ideal gas is the black one. The one I just crossed out.
Oh.
So okay.
Okay.
Let's lock that and erase everything I wrote. You see the black straight line, horizontal line there? That's for the ideal gas.
So the ideal gas increases more with temperature and
Yeah.
pressure.
Now, if you look at this carefully, what is this telling you as well? The higher your temperature, the closer you are to an ideal gas.
But why does the number of moles increase as the pressure increases for the other gases?
This is assuming that the volume is constant, I guess. All right. Again, don't think of this as number of moles. Think of this. I think that's the easiest way to just make sense of this all. This is not number of moles per se. Okay. This is the pressure compared to the volume that it occupies times the actual pressure. That's over RT. So this is basically the curve for when the temperature is changing, the uh, the pressure is also changing, and because of that, the volume is also changing. Okay.
Well, why not the temperature?
Because sorry, for a particular temperature. So these would be the curves for a particular temperature. So basically, what we're doing here is for the green curve. For the green curve, we're putting that in here in the temperature. So, and this is how the curve would look like.
Oh, okay.
All right. So, okay. All right. Let's move on to the. What's a good one? All right. Again, that last one, I'm not. I'll just be honest. I'm not so totally satisfied with the way I said it, but that's the best I can come up with at the moment. Right?
Okay.
Okay. All right. Now let's go to the last three questions. Let's do the simple harmonic oscillator problem first. Yeah.
Okay. With
Ah.
P?
That would be the one numbered 16.
Okay.
All right. Then we have the one with the C and the one from the book. Okay, let's do this last problem. This next problem here. So you're given the equation for the displacement, right? So, if you know how to do calculus, the shortcut is to just find the integral of that. Okay, so calculus shortcut, v will be equal to the derivative with respect to time of x0 sine omega t plus pi over 2, right? Okay, now which would give us x0 omega cosine omega t plus pi over 2. Okay, so I'm just giving you the option of using calculus, and because I know you've learned it, right?
Yeah.
Okay, so at this point, okay, so this is the velocity. What's the velocity of the particle at time equals half the period? Okay, I guess that's just at velocity equals half the period. So, sorry, at t equals 1/2 of the period here. Let's just do. Okay, I think we better do the other one first. So that's the way we do it with calculus, but this time we can also do this with the data booklet, right? We're just gonna go straight to the data booklet and refer to that in wave behavior. Speed. There. Actually, it's still the same. We get this. Oh, okay. We're gonna do it like this. So data booklet, we get basically the same formula. V is equal to omega x0. Same one. In this case, cosine of omega t plus phi, the phase angle, right? So our phase angle here is pi over 2, but do we need it? Not really. Now, we also need this formula as well, okay? Okay, we need to know the position at t equals 1 at that time. Sorry, at that position at this time. Okay. Uh, what is the period in, I think, yeah, we go there. What is the period in terms of the angular frequency? That's 2 pi f. Sorry. The other way. So omega is equal to 2 pi over that, right? So the period, this already tells us this is the fastest way now. We found the fastest way. The period is just 2 pi over omega, right?
Yeah.
Okay, then that's it. So, so the time that we want is half the period, right? So the time would be equal to half the period, which is gonna be pi over omega. So that's what we're gonna put into the formula right there. Okay, so that's the thing we need to realize there. Once we know, either here or here, let's just use it here straight away, right? So the velocity will be equal to omega x0 cosine of omega. Our time is pi over omega, cancels out, plus pi over 2. So we just solved that straight away. What's omega x0 cosine of 3 pi over 2? What's the cosine of 3 pi over 2? That's 3 pi over 2 is 2 pi. That's gonna be like 270 degrees, which is on the y-axis. That's gonna be what? 0? Is it? Let's double check. My brain's not braining right now.
270 degrees.
270 degrees, right? 270 degrees. And since the brain isn't working, let's just use a calculator. That's 0. So we know the velocity already. So?
Yeah. Cos 270.
So we have our answer, B. Okay. Right. Okay, I think that's done. Any questions there? Okay, if none, go ahead.
Just how exactly did we get to 3 pi over 2?
Oh, okay. So let's go back there. Okay. Okay. So we're clear where we got this part, right?
Yeah, and then we got to pi.
Okay. Now the idea now is I'll just focus on the cosine omega t part. I'm not gonna put the x0 omega anymore. Yeah. So let's use a different color for here. Let's focus on what is cosine. It says there that it's cosine omega t plus pi over 2, right? That's the equation given to us.
Oh. Right.
Basically given, right? But we know that the time is from here. That's gonna be t equals pi over omega, right? So we substitute that in. So we get cosine of omega times pi over omega. That cancels out. Okay? And then we still have to add the pi over 2. So we can rewrite that as cosine of pi plus pi over 2. And that's just 3 pi over 2.
Right, and then we multiply by the first two numbers and 0.
That's right. Okay, so cosine of pi, 3 pi over 2. Okay. Anyway, that already, like I said earlier, that's 0. Everything gets to 0, right? All right, so let's move on. Next problem. Which one? Okay, we'll do the one in the book. So in this case, we have okay. Okay, let's see here. All right. So lock that. So the mass of a typical grain of coarse sand is 12 milligrams. Calculate the energy equivalent of this mass. Oh, this one's easy. All you have to do here is just do E equals mc squared. Okay, because we're changing the mass into energy equivalent, so we have to use this formula. This will give you joules straight away if mass in kilograms. Okay, all right. Of course, that also means you just use c squared right away. So in this case, 12 milligrams is 12 times 10 to the minus 3 grams. So minus 6 kilograms, right? Okay, minus 6, and then c squared, that's just c squared. Put that in the calculator to find the energy. So c is 3 times 10 to the 8. 3 exponent 8. Square that. Oops. 3 exponent 8. And then square that. And then times 12. 12 exponent negative 6. That gives you a total energy equivalent of, that's a lot of energy if it all got converted. 1.08 times 10 to the 12 joules. Okay. That's in joules. Now, how do we do megawatt hours? This is the weird bit. Usually when we do this is in electron volts, yeah. But this is weird because of megawatt hours. Now, let's just go to the fact that we're just gonna convert this straight away, okay? 1 joule. Let's go back to here. Power equals energy over time, right? So from here, the energy should be equal to power times time. Makes sense so far, right? But here's the thing. If this were in joules and this were in seconds, this would be in watts. Okay? So going back here, so this tells us that 1 joule is equal to 1 watt times 1 second. Or 1 watt second. Okay? We're going to use this conversion to do the final solution. So this is going to give us 1.08 times 10 to the 12. And then they're exactly the same unit, so that's going to be watt seconds, right? And then we're going to convert watt to megawatt, and then seconds to hours. So we're going to convert megawatts here, and that's going to be 1 to a million times 10 to the 6 watts, okay? And similarly, we're going to change that from seconds to hours. So 1 hour is 3,600 seconds. Okay? Yeah, basically that's it. So we get this number from before. We divide by 10 to the 6, that's a million. Okay? And we divide further by 3,600. So this gives us 3.0 times 10 squared megawatt hours. Done. Okay? Megawatt hours. All right, so basically it's just a convert. For B we just don't convert, but A we need to use E equals mc squared. Okay?
Yeah.
All right, well, we have one more. Let's just finish that.
This one's, I think I already sent it before, but I forgot how we solved that, and
Yeah.
I couldn't find it.
Yeah, so let's just go back to it. Let's just get back to it. Let's see what we can do, okay? All right, so again, you have the standing wave sitting there. The solid blue line represents the wave at t equals 0. Dashed line is t equals 1/2 of the period. Blue line represents t equals period over 8. Okay. I don't know why it's not that clear when we do that. I think we need to zoom in. Okay, so again, what does it say? Solid is t equals 0. Dash line is half the period. Half the period, right? And then the third one, the blue line at t equals t over 8. Okay, I'm going to draw first the equilibrium position so it's easier to see what's happening, right? But I'll use pink. Okay. The equilibrium position, let's do that again. Hold on. Let me lock this. Okay, all right, so let's do that again. Equilibrium position should be here. Okay, and let's do that again. Okay, that's the equilibrium position, and this already tells us something. At P, you are at equilibrium. Okay, so let's take a look first. Here, a point to indicate the position of P and an arrow to indicate the velocity of P. The mark point shows the equilibrium position of a point P on the string. Okay, so that's equilibrium, right? So we're now looking for this. Now, the easiest way to do it with in terms of the period, and this is the way I always think of it in terms of the period. Okay, am I back yet to pen? Yeah. All right. It always goes from, it oscillates like this. I always think of it in 4 stages. Okay. Now from here to here takes 1/4 of the period. Each stage takes 1/4 of a period. Just always think of it like that. Okay. So so where would the position of P be at t equals 1? T equals t over 8. This thing. This is basically 1/2 of an arrow. 1/2 of 1/4. Right? So this means this should be here. Okay. So this means the position is right there. And which way is it moving? You can see that it's moving down. The whole wave is moving down at this stage. Right? So the velocity of this particle is going to be like going down. Okay.
But I don't understand why you drew the arrows that way. Like the wave is moving up and down, but
yes, that's true. That's true. Okay.
Up.
Now you always have to remember that a wave is still oscillating. Even if it's a standing wave, it's still oscillating. Okay. So that's important there. Because it's oscillating, we need to know where it is starting. And then we need to know which way it's moving at the from the beginning, right? So basically what I'm going to draw now is I'm just going to draw that half. I'm not going to draw the whole standing wave anymore, but just this part, right? And P, if we use the colors as is, it's here, somewhere here, and then we can draw the blue wave like that, right? Okay, that's the blue wave like that. Okay, so again, imagine that this particle, so which one am I going to use? Orange. Okay, so this particle here will always be oscillating here between those 2 points, right? And again, always remember that oscillation, it has to go back and forth. So you're gonna have to, if you start from here, because it says here that this is t equals 0, right? So that's where you start. So from here, the only way you can go is down, right? So that's gonna be 1/4 of the period, right? So that means again, from here to here, from the t equals 0 to the equilibrium position, 1/4 of the period. Then from equilibrium back to the other side of the wave, that's another 1/4 of the period. Okay, then that's going down. Then because of the fact that it will have to go up, that also takes 1/4 of the period, or t over 4 again. Then from equilibrium back to its original position here earlier, that's going to take again t over 4 to make the whole process the period, right? Because the period is the time it takes to go from where it was, make one full cycle, come back.
And what if we put it as t goes up as it goes up first and then goes down.
Then that means, if you do it like that, then that means this has to be where t equals 0. That's where you start. Remember, t equals 0 means you start right there.
Oh, yeah. And one question.
Go ahead.
Why is like P in the middle of the wave? Shouldn't it be on the wave?
It is. It's going to be on the wave. But remember, as part of the oscillation, P will eventually be in the equilibrium position. And that's exactly what it says right there. P is the equilibrium position of that particular part of the wave. Okay? It says so right there. Again.
Oh.
Okay? So the marked point of that's the equilibrium position of P. Right? So that's why it's in the middle. Now, that also means because it's in the equilibrium position, it is also oscillating. So we have to just go to the question here. Now we're looking for the time equals 1/8 of the period. So this tells us that this is half of 1/4 period, which also then tells us this is half the arrow. Make sense? Well,
yeah.
Approximately half the arrow. Okay. All right. So from there, all we need to do now is just mark the new positions, and let's do that with green now. So the new position would be here. The position in part 1 would be here. And because it's at the moment going down, it went down, it's going to keep going down. So the velocity is going to be pointing down. Okay.
Okay. But sorry,
Go
I
ahead.
know we're over time.
It's okay. It's okay.
So if we think about them going up and down, how do we sometimes get the answer that P moves backwards or moves forward?
It has something to do with the time relative to the period.
But how can we know how much it moves in that time when you don't have a graph with numbers? I'm asking because I remember this question, and before the answer was it moves to the left, and it's like back.
Okay.
So I don't know about
that. It was a slightly different problem then, I think. Okay, but okay, you all again the main thing you really need to do here is know where it is, or know where it starts, and then know which way it's gonna move from the beginning. The rest of it will follow with the times and the positions and the velocities. Okay, so this is what I mean. What if I make it start? What if I make it start here? It doesn't make sense to go down anymore because it's at the maximum possible position. So it has to go only up, right? So this is going to be our t equals 0 here, and it's going to go up. Then again, we do the same force phases. From its original, from the amplitude to the equilibrium, from equilibrium to the opposite amplitude position, then from that position back to equilibrium, then from equilibrium back to starting point. All of those will take 1/4 of a period.
Okay.
All right. So yeah, that's basically it. So just from there, it should naturally follow which way it should be going. Okay.
Yeah.
Yeah, I think that's it. I'm pretty sure that's not 100% satisfactory, but should be close enough for now.
Yeah.
Okay. All right. Now, last thing, because we are, as you said, we are a bit over time, but that's fine. I'm just gonna say now, good luck. Oh, by the way, before we end, have you noticed on the calendar, you booked me for like 5 a.m. here tomorrow.
I didn't realize that. It was like 1 a.m. my time, so we can change.
So I think for both of us, that's not a convenient time, right?
Yeah.
All right. So just just reschedule it now before it becomes a problem. But if you can't, let me know. You tell me what time. Okay.
Okay.
All right. Okay. So in that case, we have one more lesson. Then after that, we take a break from physics. Exam on Tuesday.
Right.
Right. So.
Okay.
All right. Okay. We'll end it here tonight or today for you. So we'll just see each other next meeting tomorrow. Yeah.
Okay.
All
Yeah.
right. Okay, I'll
Thank
see
you.
you tomorrow. You have a good day.
You
Bye bye now.
too. Bye bye.
All right. Well, sorry for those on the stream. I was doing that, but here, sorry, Anzila, sorry, this was a paid lesson, so I can't really pay attention to your questions. But uh, digital circuits, is this like O levels or IGCSE? I'm just curious, because if it is, class, okay, whatever it is, all right. At this point, if you're still there, I'm okay, but I don't think anyone's here anymore. Right. Okay. Oh, somebody's still here. 3 people are still on the stream on YouTube. Okay. All right. So, okay, this is what I can help you out with, right? With this, okay? You send me a message, and we'll see what we can do first. Okay? Send me a message over over YouTube. Okay? Is that possible though? I think it is. I'm not sure. Okay, but either way, since at this point that lesson is done, so again, I think we can end the stream here as well. So with that in mind, hold on. Is there anything else? Nothing else. All right. So at this point, we're going. So don't forget to like, share, subscribe to the channel. We're on these social media platforms we're on YouTube, Facebook, TikTok, Instagram, and Twitch. Okay, there's really nothing else at the moment. So that's it. I hope you learned something today. And in that case, either way, I bid you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world. Stay freaky, everybody. Bye bye now.